Hey everyone, in this video I'm going to talk about different strategies to deal with missing values in our data. And in particular I'm going to talk about imputation. What we mean by imputation is essentially replacing the missing values in our data set with some reasonable guesses for what those values could have been if we had observed them, okay? And of course, this is going to be based on certain assumptions and different types of strategies. Depending on how reasonable those assumptions are, imputation can be more or less effective or more or less successful. Okay, but before we start, one thing we have to think about whenever we talk about issues with missingness and how to kind of replace missing values or how to take into account missing values in our analysis is we have to kind of think about the different mechanisms that are underlying the missingness, so that are essentially determining whether an observation or a specific value is missing or not. Okay, and there are a couple of or three different main categories of missing observations or mechanisms behind missingness that we have to distinguish, because ultimately they have different implications both for our analysis if we just ignore the missingness and of how we can model the missing mechanism itself. Okay. The first kind of type of missingness is missing completely at random. And what we mean by missing completely at random is that the probability that a variable is missing is the same for all units, okay? You can think of, basically just flipping a coin for each observation or for each value, and if if it lands on head, it's missing. If it lands on tail, it's not missing. It's a completely random process that determines whether some values are included in the data set and others are not, okay? And this is the least problematic type of missingness because since the whether or not a value is observed is completely random and independent of any other variable or indicator included in our data, we can basically just exclude the missing cases without biasing any of our inferences, right? So basically excluding the missing cases, all we lose is basically efficiency. Okay, so of course it would be nice to have all those observations, but at least excluding those missing cases doesn't bias our inferences in any way. The second category or mechanism for missing observations is missing at random. Okay. What we mean by missing at random, and the kind of the notation or the labels here are a little bit confusing, but those are kind of the labels that are used in the literature. So missing at random means that the probability that a variable is missing depends only on available information. Okay, so in other words, the missingness is not completely random. It is related to some kind of characteristic, for example, age, education, or something like that. But the key is that we measure this characteristic. So by being able to measuring that characteristic, we can actually control for that and therefore also basically correct for it in order to still get unbiased estimates of whatever coefficient or whatever kind of effects we're trying to estimate. Okay, so if our data is missing at random, the probability of a variable being missing is just conditional on just depends on available information, data that we have in our data set itself. Okay, so we can condition on that, and by conditioning on that we can basically still get unbiased estimates. All right, so excluding the missing cases now does not bias inferences as long as the regression adjusts for all the variables that affect the probability of missingness. Okay, in that sense, missingness at random is kind of a similar assumption to ignorability, which we talked about in the context of causal inference. Because in some sense, both require that sufficient information has been collected, that we have all the information that we need to, in order to condition on it, in order to basically be able to ignore either the missingness or, for example, the assignment mechanism to a treatment group in the context of causal inference. Okay. The third and most kind of difficult and problematic category is missing not at random. And this can basically mean two things. Either the missingness, it depends on unobserved predictors. So again, whether or not an observation is missing depends on some other characteristics, but that characteristic itself is not included in our data. Okay, so we can't condition it on it, and so we run into problems. Okay. The second alternative is that the missingness depends on the missing value itself. And this is where we have issues, for example, of censoring. Okay, so you could think of, for example, if we're asking people about their income, about their household income in a survey, and people with higher incomes are more likely to basically not report their income. Okay, then the missingness itself is dependent on the value, and then we need to basically take additional steps to model the censoring mechanism as well. There are techniques to do that, but if we have missingness that is not at random, things become more complicated, right? They become more complicated, as I mentioned, because missingness must then be explicitly modeled. And we can't just exclude missing cases, because otherwise our inferences will be biased. Okay. So after kind of covering these different mechanisms for missing observations, let's kind of take a look at the range of possible strategies or approaches for handling missing data. Okay, and this is kind of like an overview of all the different things that we could do. Okay. On the one hand, we have approaches where we discard data. Okay, so these are missing data methods that basically that ultimately don't take into account all observations. Okay, First, we can just run a complete case analysis. So that means we exclude all units for which the outcome or any of the inputs are missing, and this is kind of the default for, you know, if you run a linear model or logistic regression with a data frame, what we're doing is usually listwise deletion. So any observation that has a missing value on any of the either outcome or input measures will be basically removed from the analysis. Okay, so that's one alternative. Depending on the underlying missingness mechanism, at a minimum we're losing efficiency, and if we don't take into account this missingness mechanism and adjust for those covariates, our estimates might be biased as well. Another alternative is available case analysis. If we have a larger set of predictors, for example, we kind of look at different subsets of a problem, predicting basically or using different predictors in subset of analysis in order to be able to use all available observations or all available values for each individual variable in order to kind of minimize the number of observations that have to be removed, right? So one example could be, you know, for example, if you just look at a basic correlation matrix of a set of variables, if you do a complete case analysis, you remove every observation that has a missing on any of the inputs on any of the variables that you consider in your when you compute your correlation matrix. If you do available case analysis in that sense, then you would only remove observations if they have a missing value on that specific variable that you're looking at in that specific correlation. Okay, so in that pair of variables. Okay, but you would still include that observation in when you compute other types of correlations. Okay, so that would kind of there are applications where you can do something along those lines, but obviously that you have to kind of find a strategy of how to include cases and how to create these subsets based on your specific application. Okay. The third option is non-response weighting. So again, we are basically removing the observations that are missing, but we're then reweighting the available data to adjust for which pieces are missing, right? So basically, we create survey weights based on the inverse of the predicted probability of having valid data, of having non-missing data. and then weight our results by that non-response weight in order to adjust for the missingness. Okay. Then there are a couple of different approaches that retain all the data. Okay, and the first four are kind of like basic, simple approaches, and the last one is then multiple imputation, which we're going to talk about in a little bit more detail. Okay, the first one is mean imputation. What we mean by mean imputation is to replace each missing value in our data set with the mean of the observed values for that variable. Okay, the advantage of such an approach, of course, is that well, we can include those cases, and we're not changing the mean of that underlying variable, right? Because we're just including the average for each of those missing observations. But obviously, we're basically making very strong assumptions. We're reducing uncertainty, and we're basically just assuming, or we're reducing variability, and we're basically just assuming that each missing observation is just equal to the mean. And obviously, that is not a reasonable assumption. Ultimately, that will lead to less variation in our input variable, or in the variable that has missing cases, and that could ultimately lead to underestimating uncertainty if we use that as an input in our variable. But it could also lead to biases and so on. Okay. Another approach is least value carried forward. This is in a case where we have, for example, multiple observations or multiple measurements for each observation. So, for example, if we have kind of a pre-test, post-test design, and we have missing values for the post-treatment value on some observations, then we can basically just use the value from the pre-treatment measure that we have and plug that in for the post-treatment measure as well. Right? Again, this involves certain assumptions that the value just doesn't change, and it doesn't take into account the potential uncertainty. Okay. In certain applications, we could also use information from related observations. So, for example, if we have a household survey where we ask, a spouse or ask the father of a child a certain question, and there's a missing value on income or something like that, and then but we do have the information from the mother, we can plug in the information from the mother as kind of a related observation to impute that missing data. Okay. Again, this is very much dependent on the specific application. Okay. Lastly, imputation based on logical rules. So this again depends on, for example, a specific, if you have specific filters in your survey or something like that, depending on your data collection and design, there might be potential ways of using basically just logical rules to impute reasonable values for certain missing observations. Okay. As you can probably imagine, these approaches all have, depending on the application, have advantages, but certainly have disadvantages as well, and oftentimes make very strong assumptions. And at a minimum, they reduce the uncertainty that we have around those missing observations, because we're basically making deterministic decisions about what that value was, right? And we at some point need to consider the possibility that there is some uncertainty around those imputations as well. Okay, and that's where multiple imputation based on statistical models comes in, right? Basically, the idea behind multiple imputation, and that's the last option here, number 5. The idea behind multiple imputation is that rather than replacing each missing value in a data set with one imputed value, depending on what rule we're using, it makes sense to ultimately replace each missing value with several imputed values that reflect our uncertainty about our imputation model, right? And then, of course, the next question is, how do we get those predictions, those imputations? And ultimately, what we're going to do is we're going to use a statistical model to make predictions and then take into account both estimation uncertainty and sampling uncertainty to make predictions in multiple kind of versions of our completed data set to take into account that uncertainty. Right? And that's basically the entire approach behind multiple imputation. Okay? The first step, as I mentioned, is to compute multiple predicted values for each missing observation, for example, based on a regression model. Okay? And then take into account both the estimation uncertainty and the sampling uncertainty, the way we talked about different levels of uncertainty in both linear modeling or in the context of generalized linear models. Okay? Then the next step is to combine each set of imputed values with the observed data to form multiple complete data sets. Okay, so basically we have not only one data set that has now all values, all missing values filled in, but we have, for example, a set of 5 iterations where, of course, the observed data stays constant. But for each of those missing values, we now have a different value that replaces the missing observation. Okay. What we do then is we run our analysis within each completed data set, right? So rather than running one model, we run 5 models for each of those imputed data sets and then combine the inferences across data sets, okay? The way we combine them is basically by taking, in the context of generalized linear models, we take our coefficients from each of those imputation data sets, and the overall estimate is then the average of the estimates across those imputations. Okay, so that's pretty straightforward. We have 5 different regression models with 5 sets of coefficients, and our overall across imputation estimate is then, for each parameter, is then the average across those imputation rounds. Okay. But the key question is, how do we characterize the uncertainty around those estimates? And in order to characterize that uncertainty, we need to take into account both the within imputation variance and the between imputation variance. So in other words, for each individual, for each one of those 5 models, we have a standard error within that data set, basically, for our estimates. But we also have between imputation as variance in terms of the kind of point estimates for each of those imputed data sets. Okay, if we basically look at the within imputation variance, we can just basically compute the average of the standard errors. So this is the standard error in one imputation data set, and we can just compute the average of those standard errors to get the within imputation variance. And the between imputation variance is then basically the variance of point estimates across those imputation iterations, essentially. Okay, both combined, according to this formula, then give us a imputation based standard error for our beta coefficient. Okay. We can do that manually. In the Q&A session, we'll go through one software example to actually go to actually compute those imputation standard errors. But there are also packages that basically allow you to directly compute predictions and compute these completed data sets in a very streamlined fashion. Okay, so if you're interested in multiple imputation, and if you have issues with large proportions of missing data, for example, make sure to check out the readings that are included on Canvas as well. In particular, the software package that is introduced there is called Amelia 2. It's basically a package for R that you can directly install and implement in order to create these imputation data sets and then run your analysis and combine the estimates across your imputation data sets. Okay, but for this, this should be enough. Again, as I said, in the Q&A session, we'll look at more software examples as well. But until then, I'll leave it at that, and I'll talk to you in our next Q&A session.